Okay, time to start. So before we conclude on the bi-elliptical, thanks to those who asked the question last time. It made me think a little more about that plot, and I was surprised that actually this is not the entire story. I don't know if you opened my MATLAB file. I spent some time trying to justify those regions in the plot that is after this. This is the bi-elliptical delta V when you do what we said. Small circle, first ellipse goes outside of the target ellipse. So you start from an inner circle. Your goal is going to a bigger one. This is your focus, the planet. And the way you do it, one impulse here goes to an ellipse whose apogee is outside of what we called RC, which is this radius. And I think we call this one RA. And this distance was RB, right? And then from here you do another impulse so that you, okay, let's be precise here. Should go outside. Do this and correct here with a third impulse, right? So if you do this, you are going from a circle whose same major axis is 2RA to an ellipse whose same major axis is higher, so you speed up, first one. Then from here, I don't know what we call this point. I don't know if I have it here. Yeah, B makes sense, RB, yeah, that's me. You speed up again because you're going to another ellipse which is even bigger, right? And then what do you do at the last point, which is point C, right? What do you do here? You slow down. You're shrinking now. The same major axis, again, for a circle, same major axis is diameter. For an ellipse is distance perigee apogee. So this distance, B to C, is less than this distance, right? So I am slowing down. So that is the last impulse. It's speed up, slow down. Now, if you want to do the other option, which is absolutely doable, I just didn't want to rush a response, and I really needed time to think about, because there is a reason why no one does it, and it's pretty simple. It just costs more, always. Let's see, yellow worked well. I think it was fine. So you can do this. You can say that B is here in the middle of RA and RC, and then do this. Whoops. And so these are still three impulses. Speed up, you're going to a bigger ellipse. Speed up, you're going to a bigger ellipse. And then another speed up, because you want to go to a circle which possesses the same major axis, which is the diameter bigger than this same major axis. Do we see that? So in other words, if you look at this expression and how you find it, everything remains the same. This term is different, because that has to do with the last delta V. And I also posted, I gave it to you as an uncollected homework to basically demonstrate those two formulas. So you have the PDF, you basically have this. I scanned my own notes. That's what you have as a solution. What happens is that the last delta V, as you go through the calculations, the last, let's see. Yeah, the last delta V, I'm just going to show you what part changes. Has a 1 over square root of alpha with a plus. What was that? I heard something. So instead, if you're going for that, you have a minus. So basically, when you put everything together, you will have a -1 that belongs to the first impulse. And here you will have a minus as well, so the minus is collected outside, and you get this expression there. So instead, last delta V will have a plus. In other words, as I have in the code, everything remains the same in that expression except, here this piece right here. So this piece that in the book is minus 1 plus square root of alpha over square root of alpha. This was the old case, right? It becomes 1 minus square root of alpha over square root of alpha. I do encourage you that you go through the uncollected homeworks once again, because that's how you prove that formula that is on the book, and that's how you prove that if you're going for an inner B point, you need to change just one piece of that expression, and that's the one. So once again, if you have done the calculations to prove these to yourself, you go back and just verify that everything remains the same in this expression except this piece. It becomes a plus 1 minus square root of alpha over square root of alpha. So if I use that only, I cannot use it in case I do something like this. It does not represent this case. That's what I'm saying. So that's why I was surprised that the book is not covering all cases. But there is a simple reason, which is if you try that, it does work. It's always more expensive than Hohmann. So there is no point in considering an inner point B. And again, these are, so I hope everybody understands here that there is no analytical proof for all of these. You find these expressions, but they depend on multiple variables. In this case, RC and RB say that RA is set, and also RC is set. So you can change B, but they enter into this expression in very non-linear ways. So intuitively speaking, if you're asking me, when is this better than this? I have no idea. I have to plot these expressions, right? No one will be able to tell you that. You can try, but people before us have tried, and they ended up plotting them. So that means you cannot do it analytically, but you can do it choosing a few different cases as an example, and that's what you get. So this has to do with the classical bielliptic maneuver where you go out and then you reach the circle. So the blue is the everything is normalized delta V, basically those expressions except the V0. Remember, V0 is the velocity on the circular orbit. Everything is normalized by that, so let's just say that that's a constant. And so the blue is the cost for Hohmann. And those lines are just a bunch of different values for beta. So basically I'm moving the point, changing beta means moving this point B, right? Because beta is RB over RA. And here I am only looking at cases where this happens, which means that I am outside with this point B, okay? What people do. And so if you plot a bunch of them and you go with very high betas, at some point you do find this intersection point, which is at about that 11.94 that they tell you in the book, right? So before 11.94, again, beta has to be greater than alpha. You do see the blue line is always below. So you do Hohmann. And then you will have to continue plotting more of these lines to actually see the other limit here, which is, as they claim, 15.58. I don't have it here, but you can clearly say that in between here, that 11.94 and that 15.58, here you need to choose. You need to see where you are, because depending on beta, so this is, I think the red one is is beta equals to alpha, or right after alpha, and then you increase beta this way. So it depends where you are, right? Which one you pick. So you give me an alpha, which is the ratio between where you want to go and where you started from, and you need to choose here what you want to do. If you, for example, choose beta, I don't know, this that belongs to this line here, it's more convenient to do Hohmann. If you choose a beta that is down here, then it's more convenient to do the bielliptic. And then after that point, at some point, you really should be obvious here that bielliptic wins. It doesn't matter how many betas you try. You can increase beta as much as you want. They will kind of converge. As you go with alpha to infinity, it means that you go into a circle that is infinitely big. So they basically become the same thing. But here, in this area here, obviously Hohmann is not winning. It's the bielliptic. Now, one comment to make that is important is that this difference is not that huge. I think I gave you another image that I found online. The amount of fuel you save for the bielliptic maneuver, it doesn't even reach 10% in the best case of what Hohmann will give you. But that 10% could be, a very important factor because you don't have that extra 10%. And thanks to whoever sent me the link for the video where they show the maneuvers to reach the ISS, and now they actually use Hohmann. They used to have Hohmann and bi-elliptical transfers. You know, the amount of fuel is an issue, and the shuttle, well, we'll get to do inclination changes. I believe the shuttle, for example, used to have enough fuel on board to do a change. For example, if you're talking about changing inclination, you could only change the orbit's inclination about up to 3 degrees, no more than that. So we're very limited with fuel. And so, you know, a 10% or 5% difference could be what decides if you can get there or not. Okay, so they are used. Even if the difference is very small, they are used. Now, this is the standard case that is in your book. So this is matching this, in some sense, this explanation here where they tell you below 11.95 for alpha, Hohmann is better. In between this number, which is 15.58, I don't know why they don't have it clearly marked here. It depends on what you choose for beta. And then above that is better. I said in my message online that below this line, where RB is equal to RC, there is nothing, in the sense that the book is only giving you the delta V where RB is greater than RC. The formula it's on the book is minus 1 plus alpha over square root of alpha over square root of alpha. This is not there. And it's kind of disappointing because they could have just said, you know, here you don't even do it because it's always Hohmann above. It's better than bi-elliptic. So that's really how you should read it. And to prove that to me, I said, you know, I'm going to create my own plots, and that's what I've done. So if you look at this one, this is now beta is always less than alpha. So I'm doing a bunch of maneuvers where I change the point B here in between RA and RC. And that's what you get. These are all different values of beta. It doesn't matter what you do. It's more expensive than Hohmann, always. So you have this MATLAB file. You can play with it. You can play with the, again, I just chosen just some values for alpha and beta. For example, I don't know what I've done here. Alpha, in the first case, went from 1 to 70. That's a huge, 70, I don't know. Unless you're doing interplanetary travel, you don't really do a ratio of 70 times your initial radius. And then, as you can see, I chose beta to start from 70. It needs to be always above alpha, and I plotted that case. And then down here, I'm doing the opposite. So I just wasn't satisfied, wasn't really sure what that plot was doing, and I found out that plot was just ignoring the other case. And thanks for asking. But that is the reason why you don't do it. It's always more expensive. Any questions on this? Is this clear now? There was a question. Yes?
I was actually, when you were talking about like the difference in delta A is really not that, delta B is really not that much. I was kind of curious. Is is it more dangerous to perform than?
No. It just takes a lot more time. Okay. If you do a Hohmann, you start here, you end up here, you're done. You're just doing half period of a given ellipse. Here you're doing basically a period of this ellipse and then another bigger one, or actually you're doing this one outside, and they're both bigger than RC. So it's going to take a long time to do it. But again, if you don't have fuel and you need to reach, so say that this is, for example, like in the video that you guys may have seen. This is the, I don't know, 200 kilometers, space shuttle is here, and this is 400, and it's International Space Station. And you barely have the fuel to do something like this. You pick the right B so that you don't use more fuel than you have. And you also want to rendezvous when the ISS is here. You may have no other options than doing a Hohmann. Maybe Hohmann leads you here, and you can still catch up with International Space Station if you do the timing right, but you don't have enough fuel. So, and actually, that video explains that that's what they do. They used to do. So when you start from the planet, there is continuous thrust up to the first initial orbit, whatever that is, and then usually it's these kind of impulsive maneuvers that correct your orbit until you reach the target ISS, for example, or geostationary orbits, which are much, much higher. So again, thanks for asking the question. As I've said, I also never stop learning, and teaching is a way to learn. As you can imagine, these are not things that we do in the lab on a daily basis. We don't do impulsive maneuvers. As a matter of fact, we do small thrust, continuous type of maneuvers, even though we don't use thrusters in our research. But we'll probably see that stuff at the end of the semester if we have time. But this is how to basically cover this. I have one more case where we do a pumping maneuver. Basically, we keep accelerating or slowing down along the velocity direction, and then we'll start a few cases where we actually change the direction of the velocity vector. And everything has been in plane so far. Out of plane maneuvers, as we'll see, are even more expensive than this. Can be more expensive. Your homework too, by the way, is out. I thought I was going to give you a hint, and that is the following. And then there is no more communication. You have to create ground tracks. There is a video where I basically do exactly what I asked you to do in the homework. So you can go back and try to see if you can understand my code from the video. I don't know. I don't think it's a good idea. But the one hint I'll give you, once you have created your software to create the ground track, do this little test. Put a spacecraft in a geostationary orbit, which means latitude equals to 0, right? So in the XY ECI plane, and put that spacecraft exactly on top of Greenwich, the UK, which means at initial time the spacecraft is wherever Greenwich is with respect to the x-axis. Are we following? The longitude of Greenwich with respect to the x-axis. And see if you get a constant 0, 0 for those 15 hours, because that's the idea for a geostationary satellite, that more or less it remains where it is, right? The ground track should be a point. So that is a test case that I encourage you to do to make sure if you don't get what you think you should get, go down to basic tests like that and debug your code. So what I'm basically saying is that if this is the ECI coordinate system x, y, and z, and the planet is here, we do know that the Earth rotates, and the Greenwich meridian, which is what we call 0 longitude on this planet, will be at any given time at a certain angle called that alpha that is changing with time. And I gave you the two functions to compute this angle. Given a date, you convert to Julian date. You use the Julian date in that other function that gives you this alpha in radians, right? So you have those. So what I'm suggesting is, in case you don't like what your software is doing, is just force a special case where this radius is whatever is the altitude for a geostationary satellite, put it right here. And if it's a geostationary satellite, it will go around with the planet, and your projection on the planet should be a point. Well, more or less, it's, plus numerical errors, but that's a good sanity check, yes?
Would it stay like the same point even if we use the J2?
Yep. The J2, which we haven't still investigated, is due to the fact that this sphere is actually, it's an ellipsoid, you squeeze at the poles, so if you are in the equatorial plane, that effect is you don't see any effect. For other inclinations, other than 0, you do see an effect due to J2, but for this case, you don't. So I've tried that case too, and it's really, if you're doing step by step what I'm asking you in the homework, yeah, you really have to zoom in to see that that point is moving. Yes?
Now you just not using the J2.
No, I think I'm telling you in the homework, use that one. It's not going to make a huge difference. Actually, no. Let me correct that. I haven't tried without J2. It should make a difference. Because it's 15 hours. It's a pretty low orbit. It's the ISS orbit at 50-something degrees inclination. You probably see some difference. Use the J2 one. Yeah. It doesn't make any difference for you. You don't even edit that function. It's there. Yeah. Okay? So that's my hint. It really boils down, doing this homework, it boils down to converting orbital parameters to state vector, which you should have done already, integrate the equations of motion, which you have done already, and now computing a couple of angles, and you have to fix this one because the Earth is rotating. But if you don't like what you're getting, do this. Actually, I think you should do this sanity check regardless. If your geostationary satellite starts on top of Greenwich, and it stays there, it's probably working okay. Yes?
Is it on top of Greenwich, or is it in the equatorial plane?
It's on the equatorial plane, well, not on top of Greenwich, right? That's a good point, because Greenwich is a little north of the equatorial plane. It's, what is the latitude? I don't know, 40-something, or 50 even. It's in, London, so Greenwich is probably somewhere here. So just put it in the meridian of Greenwich. Yeah. There's no geostationary satellite above us. They don't exist, unfortunately. Yep. Okay. Any other questions? You have 3 days. I'll be gone Wednesday. We have class on Friday. Should be plenty of time to do homework, right? Let me erase this and do the last maneuver where we change only the magnitude of the velocity, which is called phasing maneuver. I'm not sure if I need MATLAB anymore, but I probably need a projector. So Patrick is finishing up the surveys. Are they done? Okay. So I'll try to save some time and just give you the statistics, the averages, discuss those, see how I am doing according to the class. By the way, it looks like you guys are almost 100 people, 99 or something. There's still 10 people who didn't turn them in, and the deadline was Friday. So I don't know if 15 people have dropped the class after the last test. I don't think so. But there are 10 people who are not taking the free 5 points. I'm just saying, you guys should pay attention to the details. You can be as intelligent as you want, but if you don't do the deadlines, you don't get the 5 points. Sorry about that. For those who forgot, yeah, let's leave that open. So the idea is the following: basically using the fact that different semi-major axes have different periods, right? And so, just as a picture to explain the idea behind phasing maneuver, say that this is my initial orbit. I am flying on that orbit, and this is my perigee, and this is my apogee. Well, what happens if I go on an orbit with the same, again, we've done same line of ups until now, and this will be the last case. What if I do one of the two, basically orbit 1 or orbit 2? What is the period of orbit 1 with respect to my original orbit? So this one is my original one, right? Well, I know for a fact that since the same major axis is smaller here, the period is smaller. The other case, since it's bigger, the period is bigger. And so say that you are flying on this actual original orbit, but you're not the only one. There is another spacecraft somewhere on that orbit, and it's ahead of you. Say that at a certain time, your actual spacecraft is here, right? You are here, okay? At perigee, you're there. And at the same time, this is your friend, the other spacecraft, spacecraft 2, that it's ahead of you. It's on the same exact orbit. You're chasing each other, right? But you're never going to meet each other because you're on the same identical orbit. Everything is Keplerian. Everything is perfect. Nothing is going on other than r double dot minus mu over r cubed r, and so nothing changes. Well, what if I want to rendezvous with this guy now? I need to do something. There are many things you could do, but one is exploiting the fact that I can go to a smaller orbit, for example, which is faster, that will allow me to catch up with this. So a phasing maneuver is basically the following. It is a two-impulse maneuver where the impulses are equal and opposite. They occur at the same point. It's usually the way we do it. It's simply at the perigee. So basically the idea is that I am right here at the perigee. I'm going to slow down or speed up. I'm going to slow down to go on a smaller orbit of the right size so that the period on this one matches the time for spacecraft 2 to go from where it is all the way to P. So they meet at this point, and so there I have to basically banish that first impulse I gave. So basically, first impulse is here. I go on the yellow inside orbit, inner orbit, and then second impulse is here, equal and opposite to the first one, so that I go back to my original orbit. But I do it when spacecraft 2 is also in that location. Make sense? It's all about timing. So in other words, well, we'll do an example. Everything you have to do for phasing maneuvers is keeping in mind this expression here, which is basically inverting your same major axis orbital period relationship. Keep in mind that the same major axis, twice the same major axis, is r of perigee plus r apogee. And there is one more piece that we need, which is the following: 2 pi over t period times time from perigee And this is again memories. So these are the three ingredients, 1, 2, and 3, Kepler's equation. With those, we can do those kind of maneuvers where we correct a perigee, go to a smaller orbit, and recorrect a perigee to match the position of spacecraft 2. So let's actually look at an example to see how this is done. You know, I think I'm shut off the projector for now. I need more space. Yes. So this is also from your book. Just giving some numerical values here. Focus. I start on this ellipse. I'm getting better on ellipses. What do you think? That's pretty good. Okay. This is now the radius instead of the height. This is given as 6,800 kilometers. That's the perigee. The apogee. It's 13,600 kilometers. And I am right here, for example. So I am at point A with my spacecraft. And I would like to do a phasing maneuver like that one to meet my friend, which is B, which happens to be, at that particular time when I am at perigee, happens to be at 90 degrees through anomaly on the same orbit. Make sense? So what I'll do is exactly what I said. I'm going to slow down, go on a smaller ellipse. So in other words, if this was my velocity in A, I'm going to apply some delta V here, okay? That leads me to the yellow orbit. Need to find what that period has to be, which means what is the same major axis. And I'm hoping that by the time I do one revolution on this orbit, B has gone from where it is to A. Okay? And that is the same major axis relationship with period. So, let's see. What is the relationship here? If I call this orbit is 1, and this orbit is 2, my phasing orbit is 2. And this is A and B, so my T2 has to be equal to what? The period on the orbit 2. I have to find what that orbit is, right? No one is giving me that orbit. I have to find out how big it is. I know for a fact that it's smaller than 1 if I want to go faster and catch up with B. But what is the relationship between T2 and T1? It's very simple. It's a linear relationship. This is the time I spend on the yellow one, and I want that time to be the time that B takes to go from here to here. So it's basically the period of the big one minus the time from A to B. Is how much time you would take to go from 0 through anomaly to 90 degrees through anomaly. And that's why we have the Kepler's equation. Everything is sequential here. We can't really forget that some equations exist. We don't need to memorize them because, again, memorization works for a few days, but you need to know that they exist. So I have everything, or almost everything. I have T1 because T1 is going to be, if I use the inverse of that expression, I have the same major axis. Same major axis ends up being, let's see if I have it here. Yeah. If you add these two and divide by 2, it's 10,200 kilometers. So this is A1, which gives me T1. Yes, 10,252 seconds. Okay. Well, you find that right away, right? So the goal here is I need to find out what this is so that I can plug it into this expression and figure out the same major axis of orbit 2. Once I find A2, I have all the information to compute the delta V at A. Following? Yes? No? Maybe? So what am I missing? I'm missing TAB, right? How do I do TAB? From there. So TAB The time that it takes to go again from A to B on this portion of the original ellipse from the Kepler's equation is going to be equal to, let's see, T1 over 2 pi times the eccentric anomaly at B minus the eccentricity of orbit 1 sine of the eccentric anomaly at B. Remember this expression, the Kepler's equation, gives you a relationship between position and time, counting time and position from perigee. Okay? So we start always from perigee, and that's the 0 time, 0 true anomaly, 0 eccentric anomaly. What do I know at B? I do know that theta at B is pi over 2, right? It's given. And so if you recall another nice expression, I can compute EB from the following: 2 arctangent of square root 1 minus E1, 1 plus E1, tangent of that theta B over 2. Once again, don't memorize, just know that there is a way to relate position and time on a Keplerian orbit. I'm missing the eccentricity. How do you want to compute the eccentricity of the original orbit? If I gave you radius at perigee and radius at apogee, there was a way to do it. It's, should I give a name to that? Probably. Let's call this C. So C is the apogee. It's RC minus RA over RC plus RA. Your tests are open book, your homeworks are open book. Just find the way to find the parameters you need with the information you're given. Remember there was a summary kind of a table at some point. So for all the types of orbits. So this boils down to 0.33, how many 3 do I have? Too many 3's. Anyways, that's what you get for the eccentricity. So if you combine this, you get whatever the EB is. Once you have EB substituting here, you have T1, you have everything. So the time to go from A to B is going to be 1,495.7 seconds. Substituting numbers. So finally I have T2, right? T2, it's T1 minus T A to B, and it is whatever that is, 756.3 seconds, which is telling me that my semi-major axis by expression number 1 of the smaller orbit has to be 9,182.1 kilometers. So I have solved for that inner ellipse, at least what I need. Because now that I have I don't need any of this anymore. Now that I have the same major axis of the two, I can do whatever I want. I can maneuver a perigee. That's all I need. I have positions, I have same major axis, I know the energy. So at point A on orbit 1, this is what happens. You have minus mu over 2 A1 is equal to velocity in A on orbit 1 squared over 2 minus mu R1. If instead I am on the same location but I decide to fly on orbit 2, this is my expression. Solve for the two unknowns. At this point you have both same major axes. A1 was given, A2 we found it by the timing relationship to do a phasing. Find the velocities, VA and V on 1 and 2. What do you expect them to be? What is the relationship between the two? Which one is the bigger one? Of course this one, right? We said I have to slow down. which gives me the first delta V in A. If you want, I'll give it a minus, just to say that it's a retrofire. This is what I have. So the first slows me down. I go on a smaller orbit. That is the right time. I've chosen the orbit so that the time spent on it allows me to exactly meet point B, spacecraft B, right there at perigee again. And so what happens once I'm done with that yellow orbit is I'm going to apply the same delta V with a plus. So I go back to my original orbit. And so the total delta V is twice this, right? Absolute value, because that's a scalar anyways. End of the story. Make sense? That's how you catch up with something that is on the same orbit, if you need to, and we always need to. It's very rare that you approach something from a completely different orbit, even because you really want to minimize, in general you want to minimize delta V's, but even more if you're thinking about doing these burns in the vicinity of another object. These engines are pretty powerful. You don't want to fire them against the ISS. So what would be a way to minimize the delta V here? Think about what's happening here. What is driving the value of the delta V is really the difference between A1 and A2, right? If I make A2 very, very small, it's going to cost me a lot. It's going to be very fast, but it's going to cost me more. So ideally, if you push this to the limit, if A1 and A2 are the same, you're not doing anything, right? So that is really extreme. So the idea would be that if you can make T2 as close as possible to T1, that is saving delta V. How do you do that? What would be a strategy? Yes? Right, you do it multiple times. So in other words, you take this expression and you decide, you know what, I can wait more than one yellow orbit. I can wait 10, I don't know, whatever your time is. So that 10, that number of orbits divides the TAB. So you make whatever is, this difference is given. You have no choice, right? At time 0, someone told you that you were here and the other spacecraft is here, so you can't really play with the time from A to B. That is a given input, and even T1 is a given input. So these two guys you cannot change. What you can change is T2 and how many revolutions you can wait. So you basically are going to reduce as much as possible what is the difference between T1 and T2. And that is the only thing you can do, is wait for multiple revolutions. So at the limit, you can wait infinite revolutions without changing the same major axis, which of course doesn't make any sense, but that is really the idea. You can do multiple revolutions on on the phasing orbit. You of course are going to end up waiting longer, but that saves you delta V. So I invite you to do this for n equals 3, for example. Try to see what you get. You're going to get a T2, which is of course much closer to T1. You're going to get an A2, which is much closer to this. They're already pretty close, but there's still a, several hundreds kilometers of difference. And we do all these calculations with n equal 3. You're going to wait 3 times more. Not only 3 times more what we had before, because you're going to increase T2. So you're going to wait 3 times a new period, T2, which is bigger than what I found. So you're going to add a lot of time. But your delta V is going to be substantially reduced. There is no linear relationship because I'm dividing by n there, and then period and same major axis are not related linearly, as we know, and then there is the energy equation where obviously same major axis is not linearly involved. So you can't say that if you divide by 3, you're going to get 3 times less delta V. No, but you're going to get less. Any questions on these? Is it clear? So if you want a problem to solve, just redo this. Play with the n. Yeah. So I think this concludes. I'm not taking off. We still have 10 minutes. I want to discuss the surveys. This really concludes the pumping maneuvers. Friday, I really want to speed up and and do the upsline rotation, which is a maneuver where you change the velocity vector and inclination changes. And I would like to comment on continuous maneuvers, where unfortunately there is no impulses involved, and we need to integrate numerically the equations of motion. So we'll briefly touch on those, but really the solution there is using MATLAB for the most part. So if you don't have any questions on this, thanks for turning in your reviews. Who did that got 5 points. I cannot do that for the final survey, just to make sure. It's illegal if I do that, okay? I can't give you an incentive to give me the final evaluation, which is set by the university. If I give you points for that, I'll be in trouble. So, yep.
What's the last, like, what's the end of the content that will be on the exam?
Up until today, I have prepared the test. Let's just say bielliptical is included in some sense, so it's what you see on your homework. Your homework, I'm asking you a question at the end. And once again, the amount of calculations, since many of the things that we do require a calculator, if not MATLAB for more complicated calculations, most of the tests and questions I ask you, they don't require intensive calculation. That is the idea, except homeworks. So homeworks do require a little more time because I want you to develop a code. And in the process of developing a code, you learn orbital parameters, how to convert them, etc. But in the test, they need to be, of course, quicker questions. But yeah, exclude this. You can exclude this, the phasing from the test. Okay. Let me see the questions I asked you. Do you have the averages here? I'm just going to tell you what the averages are. And so these are, you're not going to see these questions at, well, you know this better than I do, right? You've done it multiple times at this point. These are not the same questions you guys get at the end. It's more questions. These, I took them from my previous job. We would do a midterm survey that was required, and these were the questions, so I didn't make them up. And so there is an overall evaluation to see if the course was fine, if I was fine, and it looks like, so everything that is above 4, it's okay. It's above average, and so I'm pretty happy. I have a 4.04 here, 4.19, so it looks overall we're doing okay. So with all the other questions, I'm not going to read them all, but it looks like, so every time I see something below 4, especially if it's in the low 3s, I say, okay, maybe I should address this issue. And so I do see the first one, 372. Some of the questions having a low score is not that bad necessarily. So let's see, 1, 2, 3. Well, okay, I'm not that fair in evaluating student performance. Okay, try to do better. But what I can do is, if I recognize that a question I asked was more challenging than usual, I have to realize that statistically, meaning if 95 people had done it right, it wasn't that confusing. So I'm trying to do that. I kind of curved that test with 5 points because some people were confused by question 7, and that is my feeling about that question. But I can't, of course, satisfy everyone. It will be impossible with 100 people. Can you imagine being evaluated by 100 professors at the same time? That would be insane, right? That's what I do. So, but that well, that's why I'm really trying to ask questions in the test that are essential and core understanding, not confusing anyone. There is no tricks here. 394 is the next one. I'm not too well prepared for class meetings below 394. Sometimes I'm not. I told you that I don't always sleep as I should. So, okay. Oh no, I'm reading the wrong ones. I'm sorry. Forget everything I said. I'm confusing them. This was the course. I'm sorry. Okay, let's do it again. 372 was this one. It wasn't about me. It was about the class. Okay, 372 is this. Not too much problem solving. Yeah, this is not a problem solving class. This is an astrodynamics class. In my opinion, there are some very well defined techniques that we learn, and then it would be nice to have a second class on astrodynamics. It would be really nice. And I do recognize that I'm trying to squeeze a lot of stuff that usually is not done on an astro class of this level, J2 perturbations. I'm doing a lot of stuff. that is sometimes considered advanced. And you guys are going to end up with a big library, MATLAB library for orbits, to be honest. So hopefully you will benefit if this ends up being your job. Okay, the 394 was actually the next one. Yeah, reviews are fair, seems like. Not exactly a 4, but 394 it's can be improved. Okay, 307, 308. No, this is still a course. What am I doing? 308 is number Patrick. I don't know how to count. 1, 2, 3, 4, 5, 6. It's not your fault, it's me. It's the sixth one. 1, 2, 3, 4, 5, 6. Okay, this is the one where if I see a low score, I'm not that concerned. If you don't think that this is more challenging than the other classes, you can make it worse if you want. But I think that's okay. It means, 3, it's average. It means it's in line with the other classes. Yeah, the idea is not to make it hard just for the sake of making it hard. Okay, then it's me. Thank you so much. 484 for the first one. We try. Next one is 386, 470. Yeah, everything is above 4 here. And thank you for the evaluation. But I guess my takeaway, I use this information to try to adjust for the rest of the semester again. It will be on tests, trying to. I still have to understand if you guys are opening the book and doing your part of the work. My suggestion is, if you don't remain again behind on uncollected homeworks, if you stay on track, the questions that I ask, especially the tests, should be like, okay, yes, I know this one, I know this one. If not, then you probably have been a little behind, but we'll try to work on making them a little more to the point, because 50 minutes is a short time. And if you have any issues, by the way, please do come to office hours. I spend a lot of hours with no one coming to my office. I don't want you to come if you don't have any issues, but you can come see me and talk about any problems. Really, that's my job. So, okay? So I'll see you on Friday. Good luck with the homework.